Hi guys! So we're starting Unit 2. How did your Unit 1 exam go? Yeah, well, hopefully. If you're wanting to retake the Unit 1 exam, you have that option. You can do retake for any exam. Go look at the syllabus and read through the steps that you have to take in order to retake an exam. Alright, let's go on to Unit 2. Okay, so in this unit, we have 5 learning targets this time. Last time we had 3 learning targets. This time we have 5. And the first of those learning targets is I can use a coordinate system to model motion and to distinguish between vector and scalar quantities. So, we're talking about motion initially. It says, how do you know something is moving, and what evidence do you need to be convinced that the object is moving? And so I want you to take a moment, write down, how do you know something's moving? Now, usually, well, we have to have something to compare it to, right? If something's just free floating out in space, we have no comparison to make, we wouldn't be able to tell if it was moving or not. But if we had something, some other object, it could move in relation to that object, okay? So that object for us usually is our background, our settings around us. We need to, in order to describe motion, state where something is at a given time, because they're going to change that position once time has passed. Okay, so when we look at this, what does the equal spacing of the dots tell us about the motion of the runner? First thing you should know about the dots is we place a dot at even increments of time. Okay, so maybe this is 1 second, then 2 seconds, 3, 4. Okay? So if the dots are evenly spaced and they have the same time interval, then his speed must be the same. He's covering the same amount of distance in the same amount of time. So if the runner were faster, how would it change the model? If that speed was constant and he's just faster, then our spacing between the dots would be greater because we covered more distance in the same amount of time. Now we need to look at scalar qualities, scalar quantities, as well as vector quantities, and what's the difference between them. Scalars describe magnitude only. So if we're talking about distance, it's like 5 miles, okay? Time, 1 hour, temperature, degrees Kelvin, and 5 degrees Kelvin, whatever. It's a magnitude. It's a value, a quantity, a number. Now, a vector contains a magnitude, like a scalar, but it also gives us the direction of that magnitude. So instead of just 5 miles, it's 5 miles north. Or instead of a velocity of 5 meters per second, it's 5 meters per second in the x direction, or 5 meters per second head west. Okay, we have a direction that represents it. So examples of this would be displacement. We talked about velocity, acceleration, or position. Okay, so take a moment and describe that difference between scalar and vector. The other important thing that we addressed in the slides was coordinate system. So whenever we're dealing with these problems, and for the vast majority of problems from here until the end of the year, we're going to have to establish an origin. We, as the experimenter looking at the situation, can manipulate and decide that this area is going to be your origin. I'm going to decide in this moment, like the moment that the runner started his run, I'm going to say that position is 0 and that's my origin. Okay, but I make that choice. Now, this coordinate system, we just have x direction for the moment, right? And so it's all linear. It's all in one direction. Now, the arrow indicates the direction of the motion, and it represents the runner at a given time, okay? The arrow points from the origin to the location of the moving object as at a given time, so that arrow is going to change as time changes. And then there's a difference between position and distance, okay? Position is in this moment where you located, and distance is the length that you traveled to get there. Now let's talk about the difference between displacement and distance. Okay? Displacement is the area in between, the distance between where the object is in the moment and the origin. Okay? So like maybe this object went over here and then it turned around and it ended here. Well, the displacement is from 0 to the ending point. Now, distance is different. Distance could be greater than that, meaning that when we look at distance, if the object went there and then it came back a little bit, then the distance would be greater than just that displacement from the origin. Do you think it's possible to have such a thing as negative position? Because if I establish that this is my origin, said right here in this spot, I'm calling that my origin, and there's some object in that origin, but then the object moves to the left instead of the right, then that would be negative position. They just went backwards instead of forwards. Okay, so suppose two runners each run a distance of 10 meters in a straight line from the origin. What is the position of each runner? 10 meters from the origin, okay? So that's a magnitude, but we don't know the direction. One of those runners could have ran in the positive x direction, and the other one could have ran in the negative x direction. Now, it doesn't also have to be linear. Let's make it 2D. Right? Now we can look at displacement in the x and displacement in the y. And then that would give us our magnitude of our overall displacement vector. Maybe a better way of thinking through it is we're going to travel some distance, so not necessarily displacement, but some distance in the x direction, and then we also travel some distance in the y, right? So we're walking, we're traveling, and then here we decide to travel this direction, so that was my distance. But my displacement is the difference between my position and the origin. So x would be my displacement. Now, this displacement here, we represent it with a magnitude, right? There is a physical length there, but also there's an angle from the origin, and that would be the direction of my displacement. And that's what makes it a vector. We have both magnitude and direction. Kind of what we were saying before, distance is different. Distance is a magnitude, but not a direction. So if I say that we travel some distance, I'm not saying what angle that traveling was happening. Like we could have gone this way, or we could have gone that way, or we could have gone this way. And all those distances are the same. So in order to make it a vector quantity, we have to also provide a direction. Okay, so a change of position with both magnitude and direction, the straight line distance between initial and final position, displacement may be negative. And then a positive scalar quantity without direction, giving the length between 2 points. And it's asking which one is distance and which one is displacement. Okay? So that one is displacement, and that one is distance. Now, true or false? If an object moves 5 meters east, it has a different displacement than if it moved 5 meters west. Remember, displacement is a vector quantity, so the direction does matter, and it would change the displacement of it, so this is true. Now, if the problem said, if an object moves 5 meters east, it has a different distance, not displacement, distance, than if it moved 5 meters west, well, that would be false. The distance of 5 meters is still the same. Okay, add two vectors. Draw to scale by placing them tip to tail. Okay, all right. So, let's say that we have vector A, okay, and then we also have vector B. Okay. When we want to take these vectors and we want to add them together to see what the resultant of the two is. The way that you do that is by placing them tip to tail. Okay, so I have my A vector, and I'm going to add my B vector. Okay, and that's how you add vector components. And then you can see this resultant here. The combination of those vectors results in, we'll call it a new vector, a resultant vector C. And you figure that out by drawing it from the tail of one end to the tip of the other vector. Okay, so they're a useful tool, and it's great when we can describe how motion occurred. Like here, if we lost our cat, and we're looking for our cat, and first we went 25 meters north, okay, and we're still looking, and we think we hear something over here, so we turn, and now we travel 100 meters east, and we find our kitty, right? And so that would be my distance that I traveled, but the displacement from the house, how far the cat was away from the origin, in this case the home, that would be the resultant vector of the two. Now, subtracting vectors is similar but a little different. Okay. So here it's saying that our resultant vector, this time they're calling it B, is a combination of C minus A. Now, instead of combining these two tail to tip, what you do is you combine them tail to tail. Okay? So I have my C vector, and I'm adding my A vector. And then the resultant vector is drawn from the head of one vector you're subtracting to the head of the other vector. So this resultant B would be right there. Okay, resultant. Okay, let's look at this one. A person walks 10 kilometers east and 5 kilometers north. Use the coordinate plane to draw the vectors. Draw the resultant displacement vector from the addition of the two. Calculate the magnitude of the resultant. Okay, so when we get back on the next video, let's take a moment and we'll go through this one together. All right.